long entrusted with the mighty hammer Mjolnir, forged in the heart of a dying star.
Really, Odin? In a star. In a star.
You are an old man and a fool!
Hello there and welcome to No Useless Questions. And can we just go back to this inner star nonsense? Like, surely everyone realises this makes no sense. I don't need to explain why making something in a star makes literally zero sense. Like, how would you get in the star? And, you know, I'm just going to cut myself off here, because otherwise I'm just going to go on an endless rant about why that's nonsense, and that's not the point of this video. The point of this video is actually talking about Nidavellir.
It's Nidavellir. That's a made-up word. What was made up?
The place we're shown in Infinity War where Mjolnir was made, which is not in a star, Odin. It's near the star, and we're going to get on to whether or not it makes sense, but it's not in the star, okay? That's the end of me yelling about the inner star thing, but it's not in a star, because that's stupid. So, Infinity War, Nidavellir, what is it? How does it work? Let's get on with that. As with most Thor Marvel stuff, Nidavellir does have a basis in Norse mythology, where it's either been called Nidavellir or Svartalfheim, where I'm obviously saying these names wrong. I'm English and I don't know another language. It's standard procedure. So Nidavellir was home of the dwarves and was an underground complex of mines and forges where the dwarves created weapons, which, as we know from Infinity War, that concept was used again, where again it was the home of the dwarves, and it was a series of forges for creating powerful weapons. Unlike Norse mythology though, the MCU Nidavellir is as far from underground as you can possibly get, being a megastructure surrounding a neutron star. Side note, Svartalfheim does exist in the MCU, but it's a separate place to Nidavellir and was shown in Thor the Dark World as home of the Dark Elves. And I would not blame you if you forgot that, because it was in Thor the Dark World and it involved the Dark Elves. So Nidavellir involves a neutron star, which is immediately going to set off warning bells in terms of, is physics going to let you do this? But what are neutron stars? So let's take it back a couple of steps first and look at a main sequence star, much like our Sun, except 4 to 8 times more massive. When that star dies, the core collapses onto itself, and the outer layers are thrust off in a violent supernova explosion. So after a supernova, we're left with that collapsed core, which collapsed under gravitational forces and combined the protons and electrons in all of the atoms to create neutrons, leaving a densely packed core of just neutrons that, in some respects, is like one giant atomic nucleus. So the neutron star that's left behind is only about 20 kilometers in diameter, which is about the same size as a city, but contains 1.4 times the mass of the Sun in that area. It's so dense that even a single teaspoon of neutron star mass would weigh about 1 billion tons. The gravitational forces created by these neutron stars are so great that it can actually bend light itself in an effect called gravitational lensing. The energy given off by the supernova can actually cause the neutron star to rotate as quickly as 43,000 times a minute. So in Infinity War, when we see Thor and co go to Nidavellir, they fly very, very close to the surface of the megastructure surrounding the neutron star. Not just the rings, but the actual sphere encompassing the star. So what we know about the gravitational forces of the neutron star means that that looks very dodgy, to say the least. So if we look at Thor and look at it as if he is stood on the surface of a neutron star, because we don't know how close he actually is to the star, but it's on that sort of scale. So if he stood on the surface of the Earth, there's a force of about 1,000 newtons acting on Thor. If he stood on the surface of a neutron star, there's a force of about 186 trillion newtons acting on him. 186 trillion. Yes, you heard me right. Trillion with a TR. And the acceleration due to gravity would be about 1.86 times 10 to the 12 meters per second squared, which, to put that into something that will mean something to normal people, is about 189 billion times the gravitational acceleration on Earth. So that acceleration is equivalent to going from 0 to 60 miles an hour in 14.4 picoseconds, which is the same time it takes light to travel 4.32 millimeters. So to have the same gravitational acceleration as the Earth, you would have to be 4.35 million kilometers away from a neutron star. That is about 2.9% of the distance from the Sun to the Earth, and that's then the gravitational force that the Earth has on you just from standing on the surface of it. So let me run a scenario right now. Let's take a person, any person. Could be you, could be Thor, doesn't matter. Let's treat them as a point mass just to make this simple, so we don't have to take into account, getting torn to shreds by a neutron star. And also, let's just ignore relativity for now. It would change these numbers, but we're not going to go into that right now. Let's take that person and put them at that distance of 4.35 million kilometers away from a neutron star. So initially, you're just accelerating downwards the same way as if you were falling on Earth, and see what happens. So 100 meters later, you'd be going at about 159 kilometers an hour. After a kilometer, you're going at about 504 kilometers an hour. After 10 kilometers, you're going at 1,595 kilometers an hour. At this point, you're still only accelerating at about the same as you were on, at the start, as you would be on Earth. So you're hearing those numbers for speed and saying, oh, you're going really fast, that'd kill you. Speed isn't what kills you, acceleration is what kills you, because that's what's related to force. So at this point, because you're still accelerating about the same as you would on Earth, you're probably fine. So let's start up a notch. We've got to 10 kilometers away from where we started. Let's just go way further, 1 million kilometers from where you started. Obviously, it's going to have taken quite a while to get there. But at that point, you're going at about 57,000 kilometers an hour, and you're accelerating about 1.7 g. So still not enough to kill you. At 2 million kilometers, you're going at 97,000 kilometers an hour, and about 3.4 g. Whether you'd have been killed by these forces at this point, unclear, because you don't know how long you've been travelling for, and when you go, when you're applying forces greater than gravity for longer periods of time, that's when it starts to do damage. That instantaneous acceleration is not going to kill you. 3 million kilometers, though, that's when you're hitting acceleration of over 10 g, at which point you can survive that for a couple of seconds. So you're dead by this point, but just for the sake of it, let's say you're not. You're travelling at 1.57 million kilometers an hour. That sounds like fun, right? Until you hit the surface of the neutron star at about 64% the speed of light, an acceleration of, as we said, about 189 billion times Earth's gravity. So in reality, what would happen if you actually went near a neutron star? Well, to put it simply, gravitational forces would rip you to shreds. Not just in your arms are getting pulled off, you'd be atomized. You literally just... It's impossible to really comprehend what would actually happen as you're ripped atom from atom. The atoms that comprised your body would be streaming towards the surface of a neutron star, smashing into it, giving out more energy than the world's entire nuclear arsenal. That is the reality of going near a neutron star. These things are mind-bogglingly, incredibly, weirdly brilliant, is the only way I can put it. It's like they're the most extreme things in the universe other than black holes. In all of this, we haven't even taken into account the fact that the surface of a neutron star is about 600,000 Kelvin. Taking into account, main sequence stars, we're talking thousands of Kelvin. This is hundreds of thousands of Kelvin. Even up to maybe even 1 million Kelvin on the surface of a neutron star. So if you're that close to it, you're just getting vaporized as well. You're getting vaporized, atomized. These sound like science fiction guns, not real things that would happen to you if you went near a neutron star. This is the ridiculousness of just, oh yeah, Thor just went to a neutron star to get a weapon. No, he didn't. He died because that was a stupid idea. It would take a lot of magic to be pulling this off. Fair play to the dwarves, because we haven't even got onto how on earth they constructed Nidavellir. That's taking incredible levels of what has to be magic. and not even in the, oh, it's science we don't understand yet magic. It's stuff that doesn't make physical sense, like we're defying the laws of physics here. So in conclusion, the scene in Infinity War makes no physical sense, apart from the bit when you take into account, yeah, magic's a thing, isn't it, in the MCU, and it wouldn't make for good plot for Thor to get destroyed by gravity. Yeah, the big bad of the MCU is physics. It's not Thanos. Thanos can't beat physics unless he uses magic. So hopefully somewhere within the rambling and ranting you've actually learned something about neutron stars or physics in general, because neutron stars are very interesting things. I'll be linking to several different sources in the description that go into way more detail about neutron stars that are there just for educational purposes and not, you know, me trying to talk about Marvel through the lens of physics. An idea I've already described as being probably terrible because, you know, plots don't really do well when you use physics all the time. So if you've enjoyed, make sure you subscribe and stick around for part 2, where I talk about the construction of Nidavellir, because I came out with way more research than I thought I was going to for this video. And make sure you ask any questions you have in the comments, because, as I say, there are no useless questions here.